Hello everybody, in Module 5 I discussed real effects of accounting disclosures. Module 5 has 6 lessons. Today I focus on Lesson 2, different types of investment distortions. In general, there are 2 types of investment distortions, overinvestment and underinvestment. And under and over, they're relative to the investment decision in the first best benchmark, which means when there is no friction in the economy. While whether there will be under or overinvestment depends on specific models. In general, I can say there are 2 rules broadly applicable to the real effects literature. The first is when endogenous variables, such as investments, they're measured with noise, which means that the exact amount of endogenous investment is managerial private information, but return on investment is common knowledge. Usually there is underinvestment. On the other hand, when the endogenous investment variables are measured perfectly, but exogenous variables such as return on investment is managerial private information, there is usually overinvestment. And this kind of model belongs to the so-called signaling models that we're going to talk a little bit later. The intuition is related to the difference between math tools for exogenous and endogenous variables that we discussed in Lesson 2 of Module 1. For exogenous variables, you do Bayesian updating. For endogenous variable, you form conjectures. First, let's look at the case where investment is measured with noise. There is a manager. The manager privately chooses the amount of investment K. The firm value is theta equals K plus some random noise epsilon. Epsilon is normally distributed mean 0 and variance sigma epsilon squared. The investment incurs a quadratic cost. The markets cannot observe K, but can observe a noisy report of K. I say Y equals K plus epsilon, where epsilon is some normally distributed random noise, independent of epsilon. The market sets the price after observing the report to be the expected value of theta conditional on Y. The manager is going to choose the K to maximize the expected value of P at day 0 minus the investment cost. In the first best, K is observable, which means P would equal to K. And so the manager is going to choose K to maximize K minus 1/2 K squared, resulting in the first best choice of K to be 1. What if K is measured with noise? Because K is endogenous, the market is going to form a conjecture about the manager's choice of K. And let's say the conjecture is K hat. Of course, in equilibrium, K hat would be consistent with the manager's actual choice. In this case, Y is a noisy signal about endogenous variable K. Noisy signals about endogenous variables have no information content because the market is going to attribute the discrepancy between Y and the conjecture to the measurement noise, which means that the market is going to set the price to be equal to K hat. So the manager is going to choose K to maximize K hat minus 1/2 K squared, because K hat does not vary with K. That results in the optimal investment to be 0, which is smaller than the first best choice. So there is severe underinvestment. The intuition is that because the market forms a conjecture about the manager's endogenous choice, this conjecture is fixed and does not vary with the manager's choice when the manager is making a choice. So the manager's marginal benefit of investments is smaller than the first best when the market can directly observe manager's choice of investments. In this case, it's actually 0. So this results in underinvestment. Now let's look at the case when K is perfectly observable. But let's say some economic fundamental R is unobservable. It's managerial private information. Because the market does not observe R, we can assume that the market has some prior distribution of R. But we are going to see later, this is not needed. So the firm value is R plus K. The investment incurs a cost of 1/2R K squared. So higher R means, first, firm value is higher. Second, the marginal investment cost is lower. So higher R can be thought of as representing higher fundamental. The market observes K perfectly. And the market is going to set price equal to expectation of R plus K conditional on the market's information. The manager is going to choose K to maximize the expected price minus the investment cost, conditional on K and manager's private information R. On the first best, the market observes R. So P equals R plus K. And manager is going to choose K to maximize R plus K minus the investment cost. So the first best investment is K equals R. When the market cannot observe R, they're not going to be naive. They will try to infer R by stepping into the shoes of the manager. They're going to infer what R is from the manager's choice of K. This is similar to you're trying to infer your opponent's cards from his or her actions in Texas Hold'em that we discussed in Module 1. We focus on fully revealing equilibrium. Fully revealing equilibrium means that the market can perfectly infer R from the manager's choice of K. This also implies, in this example, K is a strictly increasing function of R. Because K is strictly increasing function of R, whenever you see K, you can invert the function of K to get what R is. Alternatively, this setting can also be interpreted as the manager using his or her choice of K to signal the private information of R, which is where the name signaling model comes from. The first paper on signaling models or signaling games is Spencer's 1973 QJE paper. In that paper, workers use the observable education level to signal their unobservable talent to employers. If you're interested in the signaling model, you can take a look at this paper. There are two ways of solving this problem. First, guess and verify. Second, use a mechanism design approach, similar to the approach we used in solving adverse selection models in Module 3. And this is because in this setting, the manager has the private information R, which is similar to the adverse selection models when the agent has some private information. Let's first use the guess and verify. We're going to guess and later verify that K is a linear function of R. So K is BR for some B that is endogenous and will be determining equilibrium. When the market observes K, because they know about this decision rule, K equals BR, they're going to infer that R is equal to K over B. So they're going to set the price to K over B plus K. They cannot observe R, so they're going to use K to infer R. The manager is going to choose K to maximize the price K over B plus K minus the investment cost. The manager takes price as given, but the manager knows about the investment cost because the manager observes R. First of all, the condition is going to result in the optimal investment being a linear function of R. Matching coefficients can solve for B. You can see that B is actually bigger than 1. So in equilibrium, there is overinvestment. The investment is more sensitive to R than the first best. The intuition is similar to the intuition that we discussed for adverse selection models in lessons 5 and 6 of Module 3. High type managers, in this case managers with high R, they're going to distort their investments to prevent managers who observe low R from mimicking. In this case, they're going to choose to invest more than the first best. For low type managers, for managers with low R, this will be too costly because when their R is low, overinvesting would significantly increase the investment cost. We can also use the mechanism design approach to solve this problem. The mechanism design approach borrows insights from the adverse selection models. Because R is the manager's private information, you can design a mechanism of KR and makes it incentive compatible for the manager who privately observes R to choose KR rather than choose the schedule K for some different R prime. That means if the manager who observes R but chooses some other investment schedule, let's say KR prime, they would be perceived by the market to be of having observed R prime. And their payoff function would be market price, which is based on R prime plus KR prime minus the investment cost. But the investment cost is 1 over 2R KR prime squared because R is observed by the manager, it's the manager's true type. And incentive compatibility would require when the manager observes R, the manager is better off choosing KR rather than KR prime for some other R prime. We therefore have a continuum of incentive compatibility constraints as the continuous type adverse selection models we briefly discussed in Module 3. We can show that this continuum of comparability constraints are equivalent to a differential equation and a monotonicity condition. If you want the technical details of how the equivalence is established, you can check Myers 1981 or Canodian and Lee 1998 JAR paper. We're going to discuss the JAR paper in the next lesson, but we're not going to discuss the technical details of this equivalence. In this simple example, you can still use guess and verify approach to solve the differential equation, but in general, you need more advanced technical tools to solve for the differential equation. So to conclude, when we talk about investment distortions, it has over and under investment. And here is a general rule of thumb for over or under investment. If the endogenous choice is not publicly observable or observed with noise, we usually have under investment. If the exogenous variables is manager's private information, but the endogenous choices are observed, we usually have overinvestment, similar to what we have in classical signaling models. However, specifically whether there is over or under investment, ultimately it depends on the specific setting and specific informational frictions of the setting. Those are rule of thumb, they're not universal rules. To test your understanding of this lesson, you can find a review quiz of this lesson on the link provided in the slides. Thank you very much.